Okay, our Module 11 videos are next. And this one is another one too, where I think it repeats some at the end. So we actually have fewer than we thought, maybe, hopefully. We're going to start with domain and range from the graph of a quadratic function, which is just a parabola. Quadratic functions are the same thing as parabolas. Okay, and that whole domain and range strategy that I showed you before works for this. So look at an example here. Okay, so suppose we have a parabola that opens down and we have the vertex at -1, 2. Okay, and goes through these points and opens down roughly, right? Okay, so remember the domain is all of the x values. And the range is all of the y values. So like if you're able to make a list of every point on this parabola, the domain would be all of the x values that you used, your range would be all of the y values that you used, okay? But we know that you can't do that because there's infinite points, and no one's got time to do that, right? So the first thing we're going to do is your domain. Remember I talked about if you take a steel plate, okay, parallel to the x-axis, and you squeeze that steel plate and push all the points, okay? So anything that's above the x-axis would drop to it. Anything that's below the x-axis would be pushed up against it, okay? And what's going on those ends there? Those arrows even get pushed up, okay? So what we have now is that number line, and all the points on the number line. So it's everything, right? You have a solid segment with arrows on the end. Your domain is -infinity to infinity. And here's a hint. Your domain for any quadratic function is -infinity to infinity, okay? Your range, we'll do the opposite. So we've got our steel plates parallel to the y-axis and squeeze them in, okay? So any points that were to the left get pushed in. Okay, so even this top here, here's the vertex of your parabola. These, we even have like 2 points that get pushed in over here, right? But it doesn't matter, it's just going to be solid. And then anything that was to the right also gets pushed in, okay? So keep an eye on that vertex that got pushed in, and then down here the arrows get pushed in, okay? So here we have y, the biggest y value is 2, and then we have everything below it. So -infinity to 2, and we're going to include the 2, okay? And I'll give you a hint too. A parabola that opens down will always go from -infinity to the y value of the vertex. And if it opened up, it'd be the y value of the vertex to +infinity, okay? Next one, we have finding slopes of lines parallel and perpendicular to a line given in slope-intercept form. Okay, so that's going to be nice because if it's in slope-intercept form, we see the slope. Okay, parallel lines have the same slope. Perpendicular lines, slopes are opposite reciprocals. So that means one will be positive, one will be negative, and that means you also, a reciprocal is if you flip a fraction, switch the numerator and the denominator, okay? So if we have y equals 2x minus 3, the slope is 2. Your y equals mx plus b, okay? A parallel line, slope is 2. And a perpendicular line, slope is opposites would be negative and reciprocal. So 2 is the same as 2 over 1. So we'd have 1 over 2. Okay, so you just flip it. Whole numbers are just like over 1. Okay, so again, if the slope is 2, treat it as 2 over 1. Okay, and that's it for that one. Next one. We have finding slopes of lines parallel and perpendicular to a line given in the form ax plus by equals c. So I'm not sure how Alex does this. I'm not even going to look, but you want to get it into slope-intercept form. So if we have the example x plus 7y equals negative 3. And by the way, if you didn't watch the previous section of the video, you guys watch the one that's up here that explains the parallel and perpendicular. Okay. So we're going to subtract the x. So 7y is negative 3 minus x. And we're going to divide everything by 7. So y will equal negative 3/7. Now be careful. We're dividing negative 3 by a positive 7, and we're dividing negative x by positive 7. So the negatives don't go away. Okay. And I wrote that, I didn't write it as x over 7. I wrote it as 1/7 x, which is the same thing, but that gets me to clearly see the slope. Okay. So my slope here is negative 1/7. So the slope of a parallel line would be the same. Okay, and then the slope of a perpendicular line would be the opposite reciprocal. This is going to be positive, and we're going to flip our fraction. So right now we have, the fraction is 1 over 7. We flip it, it's going to be 7. Okay, so make it positive 7. All right. Next one, identifying parallel and perpendicular lines from equations. Okay, so in this one, you're going to be given equations of lines in different forms. So your best bet is to get them all into the same form. Okay, your y equals mx plus b is basically the way that you want to go here. So we might have line 1, which is 4x plus 6y equals negative 8. We'll have line 2, which is 2y minus 3x, or sorry, equals, let me erase that. Equals negative 3x plus 7. And then we'll have line 3, which is y equals negative 3/2 x minus 3. That's what we want, right? Your slope there is negative 3/2. Okay, so for line 1, we're going to subtract the 4x from both sides. And we'll have 6y equals negative 8 minus 4x. We'll divide everything by 6. So y is negative 8 over 6 minus 4 over 6x. And we'll reduce. y equals negative 4/3 minus 2/3 x. Okay. So then the slope there would be negative 2/3. Okay. And then line 2, divide everything by 2. That's all you need to do. So if y is negative 3/2, x plus 7/2. So there the slope is negative 3/2. Okay? And so then they have you make the different combinations here. So just look at the slopes. Line 1 and line 2. They're not parallel because the slopes aren't the same. They're also not perpendicular. They are reciprocals, but not opposite reciprocals. So they're neither parallel nor perpendicular. Line 2 and line 3, okay, those slopes are the same, so they're parallel. And then the last combination is line 1 and line 3. And again, they're reciprocals, but not opposite reciprocals. So they're not perpendicular. They're not the same, so they're not parallel, so they're neither. Okay. Next one. We have a little different one here. Writing and evaluating a function that models a real-world situation, and they're calling this advanced. Okay, so in this one it says Donna is a software saleswoman. Her base salary is $2,100. I hope that's not yearly. And she makes an additional $70 for every copy of Math is Fun she sells. That sounds like a great piece of software. Okay, let P represent her total pay in dollars. N is the number of copies she sells. Write an equation relating P to N. And then use it to find her total pay if she sells 22 copies. Oh, you guys got this. Okay, so remember, this is going to be y equals mx plus b. B is kind of that initial value. Okay, and then m is how much it's going to be a rate. Okay, so her initial base there is 2100. Oops, I suppose I should use P. Oop. And then her rate is $70 per copy. So 70 N. Okay, I think you guys get that okay. And then if she sells 22 copies, P of 22 will be 70 times 22 plus 2100. Okay, so we're just going to multiply that out. And that comes out to be $3,640. Okay, so you guys got that. All right, next one. We have an application problem with a linear function finding a coordinate given 2 points. Okay, so this one says the credit remaining on a phone card in dollars is a linear function of the total calling time made with the card in minutes. Okay, the remaining credit after 33 minutes of calls is $24.72, and again, that's left on the card. So basically, if you guys don't know what they're talking about, I used to have to do this in college. I would get a calling card. As a card that I could make long distance phone calls with. So if I use that card to call, there was a certain balance on the card, and for every minute you used, the balance went down. Okay, and that's how we made long distance phone calls back in the olden days when I was off at college. There you go. So after 57 minutes, there's only 20.88 left. Okay, so we're supposed to figure out what is the remaining credit after 74 minutes. Okay, so we could do like a little bit of guessing and checking here. You might be able to come up with something. But we're going to start just trying to make an equation. Okay, so think about how this model would look. The amount's going down. Okay, so whatever we start with on your card would be your y-intercept, so your starting balance. And as time goes on, the balance goes down. Okay, so one reason to just draw this is figure out what you're going to use for x and y. Okay, so your time will be the x and your balance will be the y. So when we come up with our slope, we're going to have the difference in the y, so the difference in the balances. So 20.88 minus 24.72 over the difference in the times. So 57 minus 33. I don't have a calculator handy with me right now, but let's get it here. It'll be 384 for every 24 minutes. Okay, and that comes out to be 16 cents per minute. Okay, so there's a few ways that you can do this. You can figure out how many more minutes from 57 you are. So 57 to 74 is another 14 minutes. No, 17 minutes, sorry, 17 minutes. Okay, so for another 17 minutes, it's 17 times 16 cents. Okay, it's another 272 off. All right, so if at 57 we're already at 20.88, another 17 minutes is going to be 20.88 minus another 272. So we're going to have 18.16. There we go. Okay, it's probably the easiest way to do it, would be like that. All right. Okay. Next one, we are going to do, okay, moving on to something a little bit different here. We're going to graph some absolute value equations. And we did this in Algebra too, so it should be a nice little review. It was one of your function transformations. Okay. So we're going to graph y equals 4 times the absolute value of x. Okay. So if you guys remember your parent graph, please remember your parent graph. Tell me that you remember that. Okay, it had the vertex at 0, 0, and then we went up by ones. Okay, so if you remember that A is your stretch factor. Okay, so if A is greater than 1, I should say the absolute value of A is greater than 1, then you're going to have steeper. And if the absolute value of A is less than 1, it's going to be fatter. Okay, A is kind of like a slope. It's kind of like the slope of each side. Okay, so we start out with a slope of 1, and then to the left it would be negative 1. If A is less than 0, remember we flip it. Okay, so I'm just going to use a different color here. If we have 4 instead of 1, that just means that when we go over 1, we go up 4. Okay, oops, not quite to scale. Okay, but just remember that's your stretch factor here. And that's it. So, you can still get the 3 good points there like that. Okay, and again, if it was negative, it would flip it upside down. That's pretty much it. I don't even think that they give you any fractions in this one, or any that are less than 0. Okay, the next one is graphing a parabola. So another one, we're revisiting your parent functions here. Graphing a parabola of the form y equals ax squared plus c. Okay, so remember your parent function here again. Goes through 0, 0, 1, 0, and negative 1, 0, just like an absolute value 1, but it's curved instead. Okay, A is still a stretch factor. So again, if the absolute value of A is greater than 1, you're going to get a skinnier parabola. And when you go, oops, I don't know why I put zeros there. These should be ones. When you go to the right 1 from the vertex, instead of going up 1, you go up A. Okay, so if we go up something that's more than 1, it's going to be skinnier. The absolute value of A is less than 1. It's going to be fatter. Okay, and then again, if A is less than 0, we're going to flip it. Okay, C is your vertical shift. Oops. If C is greater than 0, you go up. If C is less than 0, you shift it down. Okay, so let me get a good example here. All the examples that are coming up for me, A is 1. So that's kind of weird. So I'm just going to leave it like that. If you get something different that you need help with, let me know. But they're giving all of these with A being 1. Okay, so all you need to do is shift those points down, right? This is a vertical shift of negative 1. So rather than having a vertex at 0, 0, it's at 0, negative 1. Okay, since the stretch factor didn't change, I will still move right 1 and up 1 to get to 1, 0, and left 1 and up 1 to get to negative 1, 0. Okay. Kind of abbreviating this a little bit because it is just a little review of Algebra 2, but let me know if you need more than that. Okay. Next one, kind of jumping around, back to absolute value now. Graphing an absolute value equation in the plane. And they're saying this is basic. Okay, so let me take a look at some of the examples that they're doing here. They're giving you a number out front. Oh, they're giving you a couple different things here. Okay, maybe we'll do a couple. So remember you have y equals a times x minus h plus k. If you remember that from Algebra 2. Okay, so again, this is your stretch factor. I'm not going to go over that again because we just did. And this is your vertical shift. And then remember, h is your horizontal shift. It's a little bit misleading because it's already negative. So if you have like x minus 2, h is positive, and we move to the right. If h is greater than 0, then we would move to the left. Okay, so they're not going to do, I don't see all three of these at once occurring, but we'll do a couple examples here just to refresh your memory, and it'll help you with your parabola ones also. So y equals -4, absolute value of x plus 2. Okay, so this is going to be upside down because the 4 is negative. It's going to be stretched by a factor of 4, and we're going to shift it up 2. And remember, your parent looks like this. Okay, and again, the points 0, 0, 1, 1, and -1, 1. Okay, so think about all of these things kind of occurring. We're going to shift it up 2 and flip it upside down. So the vertex will be at 0, 2. Okay, and it's going to open down. And when I move left or right 1, I will move down 4. Okay, so I'll have the point 1, -2, and then the point -1, -2. Okay, and before you submit, just make sure you've checked all of those things. It's upside down, it's stretched by a factor of 4, okay, and I've also shifted it up 2. All right, we'll do another one here that has the horizontal shift. So this one is y equals 3, absolute value of x minus 5. Okay, so this is, it's still going to open up, but it's still stretched. And we have x minus 5, so h is 5. Okay, so h is positive. Remember, when it's associated with the x, it's the opposite of what you would think. So we're going to move it right 5. Okay, so we're going to take our vertex that was at 0, 0 and move it to 5, 0. And then since the stretch factor is 3, I'm going to move right 1 and up 3. Okay, so that would be at 6, 3. And I'm going to move left 1 and up 3. So that would be at 4, 3. Ooh, kind of looks like a fox. Or a badger, maybe. There you go. Okay. All right. Moving along, because now I think the next one is to do that with the parabola. Okay, so all of these same things apply to a parabola. Okay. So we'll do another example with a parabola. We don't need to spend too much time on it. Graphing a parabola of the form y equals x minus h squared plus k. Okay, so again, all of the things that I just said about absolute value graphs apply to parabolas. It's just, instead of connecting it with a v, you connect it with a u, right? It's just the shape, okay? So if we have an example, y equals x plus 1 squared minus 3, that means it's going to move left 1 and down 3 from its parent graph, okay? So, and from what I can tell here, they don't give you any stretch factors out front for these. Okay, so we're just going to put our vertex, which would normally be at 0, 0. It's going to be at -1, -3. Stretch factor is the same, so I can move right 1, up 1. So it'd be at 0, -2. And I can also move left 1, up 1. So I'd be at -2, -2. Okay, and so I'll get that U shape to it. Okay, that's it. So we're just kind of revisiting those Algebra 2 transformations. Okay, next one we have a square root function. another one of your parent graphs. So they're all coming back. Oh my gosh, if you saved your interactive notebook, you are set. I told you to save it, guys. Did you save it? Save that unit circle. You never know when you're going to need it. All that good stuff. Okay. And for these, this is plot 4 points on the graph. The leftmost point and 3 additional points. So, whoops, I'm going to get a different one here just to make sure. See what types of transformations they're giving you. It looks to me like they're only giving you vertical shifts here. Okay. So f of x is square root of x minus 2. Okay. So again, go back to your parent function. Your parent function looks like this. Okay. And we'd have the 0.00 and the 0.11. This is asking for 3 additional points, so we can keep going. Stick with, right, this is f of x is the square root of x. So don't try plotting the next point at 2 because you don't know what the square root of 2 is, right? We would want to do 4, 2. Okay, and then we want to do 9, 3. Those would be our 4 points. That would be the easiest ones to get. Okay, so now this one, we're shifting it down. So we can take every single one of those points and just move it down 2 units. That's all you need to do. Okay, so 0, 0 would be at 0, negative 2. 1, 1 would be at 1, negative 1. 4, 2 would be at 4, 0. 9, 3 would be at 9, 1. Okay, so I literally just took each of those 4 points and moved them down 2 units and try to maintain that same shape. It's just my scale's off by a little bit between the two. Okay, that's all you're going to do. Okay, so use this parent graph and just take a look at what kind of shift they're asking you to do. Okay, next one, graphing a cube root function. Another one of our parent functions. Okay, actually no, cube root wasn't one of your parent functions, right? Graphing a cube root function. It's actually the inverse of the cubic function. Okay, so you've seen something similar. Let's do our parent. I don't know if you guys do cube root functions in pre-calc. Okay. But your parent function is still 0, 0. And then we have the point at 1, 1. The cube root of 1 is 1. Okay. And negative 1, negative 1. The cube root of negative 1 is negative 1. So this cube root graph kind of looks like this. It's like your cubic function, but it's the inverse. So it is, oh, that didn't draw in very well. Okay. So it looks like your cubic function on the side. Okay. So then when they give you one like f of x is cube root of x minus 3. Okay. They are telling you to plot, it looks like 5 points that they want. So they want the 0, 0. Okay, and then they want the 1, 1 and the negative 1, 1. But the next easiest number to get a cube root of is 8. So we'd have 8, 2, and negative 8, negative 2. Okay. So now what we're doing here is we're shifting down 3. Okay, so we can take each of our 3 points, or sorry, our 5 points actually, and move them down 3 units. Okay, so the point that was at 0, 0 will be at 0, negative 3. The point that was at 1, 1 will be at 1, negative 2. The point that was at 8, 2 will be at 8, negative 1. Okay, and the point that was at negative 1 will be at negative 1, negative 4. And the point that was at -8, -2 will be at -8, -5. Okay. There we go. So you're just, again, shifting those points. And it keeps not connecting for me. Okay. The next one is matching a parent graph with their equation. Okay, so this one, let me see here how they're having you do this. For each graph, choose the function that best describes it. Okay, oh, these are literally just parent graphs, no transformations. Okay, these are going to be nice and easy because you guys have seen these before. All right, so we have some of your parent graphs, y equals x, which is linear, y equals x squared, which is quadratic, y equals x cubed, cubic function, y equals the absolute value of x, which is the absolute value function. You guys might remember, oops, y equals 1 over x, which is your hyperbola. And y equals, I'm not sure if we did this in algebra. I don't think we did this one in algebra 2. 1 over x squared, which is similar to the hyperbola, but it's 2 branches on top. Okay. Let me see if I'm missing any that they might have. Oh, they also give just y equals 1, which is interesting. They just give you a horizontal line as one of the parent functions. But otherwise, I think that's it. They've got 8 of them. Which one am I missing? 1, 2, the absolute value. Oh, the square root one. Y equals the square root of x, which looks like that. Okay, so this is just literally matching these then. You guys should be, basically just gave you all the answers right there. Okay, so you guys should be pretty good with that. Next one. We have translating the graph of a parabola. 2 steps. And I mean, I think we basically have already done this one. You're getting pretty repetitive here. Okay, they're just having you change where the vertex is. So this one is going to be very similar to this one. Okay, this is basically the same thing. All right. I don't think you're going to have any issues with it. I'll give you one more example, I guess, just in case. They just have you move a graph that's already there, I guess. So this one, they have y equals x minus 5 squared minus 4. So if you remember, this means you go right 5 and down 4. Okay, so your vertex would be at 5, -4. And then we can go right 1, up 1. That put us at 6. Oops, that should be a -4. There you go. 6, -3. We can go left 1, up 1. And that would put us at 4, -3. Okay, and then just, there's your parabola. Okay. And the next one I feel like we kind of already did too. This next one is how the leading coefficient affects the graph of an absolute value function. Okay. So we're going to talk about if it opens it up or down and if it makes it narrower or wider. Okay, so if we're talking about y equals a absolute value of x, just like we did above. So if a is less than 0, it opens down. If a is greater than 0, it opens up. If the absolute value of a is greater than 1, it's narrower. Narrower. Here. This one would be down. This one would be up. Narrower. If the absolute value of a is less than 1, it'll be wider. Okay, good thing I think we're on our last one because it's getting bad. All right, so they give you 3 functions and they want you to tell if it opens up or down. It wants you to choose the widest one. It wants you to choose the narrowest one. Okay, so the ones that they give you to work with are y equals 2/3 absolute value of x, y equals 3/4 absolute value of x, y equals -3 absolute value of x, and y equals -2 absolute value of x. Okay, so these first 2 will open up because a is positive. The last 2 will open down because a is negative. The widest one will be the one with the lowest absolute value of a, the a value that's closest to 0. Okay, so we have our candidates here are 2/3, 3/4, 3, and 2. Well, the one that's closest to 0 is 2/3, so it will be your widest graph. Narrowest will be the farthest from 0, so that's going to be your -3. Okay, so the widest will have the absolute value of a closest to 0, and this one, the narrowest, farthest from 0. Okay, and now it looks to me like the remaining ones that I have listed, we have already done. So we are done with the Module 11 videos here then.